known to many of you. I think this is the largest seminar we've had by far, doubles our previous records. And I really do think that this reflects the esteem that we all hold Michael in as a colleague, a researcher, a friend, and I know that family are online too, so family. Some of the reasons we value Michael relate to his career history and his skills. So he started off as a land surveyor and in fact is still authorised as a land surveyor in Queensland. And I think that's changed how he looks at science. He surveys the scene and then he looks in detail at different parts of the scene. And he started doing the science aspects of his career after 12 years as a land surveyor. He moved to Perth, where he concurrently did his PhD at Curtin University and also the Department of Agriculture in Western Australia. And that's where he started really looking at water and satellite data. We were lucky enough to have Michael move to ANU in 1996, and he started off in the ecology department at the Research School of Biological Sciences. And he still holds a joint appointment with now Research School of Biology and RSES. Sometimes I wonder how Michael has time to do his science because he has a fairly big administrative load as well. He's the node leader for both the Climate Systems Science Centre of Excellence, as well as the Climate Extreme Centre of Excellence, working as the theme manager for the Drought Extremes part of that Centre of Excellence. Anyway, we're all here to hear about Michael's take on drought, bushfires and climate change. So without further ado, I would like to welcome Michael to take over the microphone.
Thanks, Penny. I assume everybody can hear me. So when I first put this seminar topic forward, it was in early February, and the popularity of the Earth Science seminar series was that I couldn't get on until now. And of course, a lot's happened since then, but that's a picture of people sitting at Mallacoota waiting to be picked up by the Royal Australian Navy. So basically, people were thrown off the continent by fires into the ocean. And the fires started in Queensland in July, and they burnt pretty much with latitude. So the time of the fires corresponded to the latitude, finishing in Victoria in February. And if you go onto Google Maps and you look at it at a certain scale, you get all the green bits on the left there, and those green bits are national parks and state forests, and that's pretty much where the fires were burning. A little bit of private land, but mostly in national parks and state forests. There's a perception surrounding these fires that it's becoming hotter and drier, and there's more droughts, higher temperatures causing more droughts. And I've heard this many times: if that's what you get from 1 degree of warming, what will it be like with 3? Is it hotter? Absolutely yes. So all of the data in this talk is straight lifted off the Bureau of Meteorology website. And so that plot shows time on the x-axis, the mean temperature anomaly on the y-axis, and it shows that 2009 was the warmest year in the instrumental record, which begins for temperature in 1910. And 2018 was the second warmest year, 2017 was the third warmest year, and so on. So there's no doubt it's hotter. But for those who don't know the poem Said Hanrahan, straight after this seminar, or even if you get bored during the seminar, go on Google it and read it, because it is an incredibly insightful sort of summary by who was at the time the Catholic Bishop of Goulburn and the Riverina, Patrick Hartigan. And it pretty much summarises the Australian experience. It's different from Dorothy McKellar's My Country, which talks about droughts and floods. Said Hanrahan put fire in there. And that's the origin of the famous saying, we'll all be ruined. Irrespective of the fact that we all know that there are droughts and fires and floods for that matter, there remains a very widespread perception that climate change was the cause of the fires. And in fact, this statement pretty much sealed it. And the quote at the bottom, it's on fire because the temperatures of the earth are increasing. So at that statement, it was a done deal. The funny thing is to someone like me, it wasn't actually obvious what the role of climate change is in those fires, and that's the basis for this talk. And the question we're going to be looking at is, what is the impact of a changing climate on those fires and what might happen in future? This is just straight lifted from Wiki. For some reason in Australia, we pick a day of the week and we put an adjective in front of it, so it's either black, red or ash. For the fires that just finished at the start of this year, they were so extensive and went for so long that it's black and it's for a whole season, so the black summer. And in fact, that's the rainfall decile from 2017 to 2019 for that 3-year period. And for large areas of Southeast Australia, it was either the lowest on record or in the lowest 10% of years. So there's no doubt it was very dry. And it's hot. So New South Wales, the question, we know it's hotter, has it become drier? And this actually all depends on how you define drier. So one of the popular plots that I see is this one, and it's the trend in rainfall from 1970 to today, calculated for each part of the country. And it shows that a large area of Eastern Australia has got drier, and a large area, or a smaller area of Southwest Australia, and then an area of mostly Western Australia and the Northern Territory have got wetter. And for those who know about rainfall trends, your immediate reaction is, Eastern Australia is just like Perth. And everybody knows that the rainfall in Perth has gone down a lot, and it's gone down so far that the major water supply in Perth is now desalination. And that's the time series for Perth. You don't need to be a statistician, you can just see it. And that solid line on the plot, the black line, is available. The Bureau of Meteorology calculate that for you. So it shows that in Perth, there's less rain now than there was in 1900. It's very clear to the naked eye. It's actually statistically significant, and it's actually non-stationary. So the rainfall in Perth is now really quite different to what it was in the first half of the 20th century. You do exactly the same plot for New South Wales, and that's what you see. So in New South Wales, it turns out that averaged over the whole state, there's a slight upward trend in the rainfall. So it's nothing like Perth at all. So it's not a big trend, and it's actually not statistically significant. And that means that the year-to-year variability is much larger than the trend. So what's going on? So on the left-hand plot, we've got the original map you see. And on the right-hand plot, I've calculated the linear regression from 1970 to 2019 and put it on top. And that's actually what's been shown on the map. So it's not a really good representation of the rainfall, mainly because the rainfall is so noisy. So what to do? So we can actually, this is work done by Anna Ucola, who's a research fellow at ANU and in the Centre of Excellence for Climate Extremes. And it was published at the end of last year, and it's about just what are the rainfall trends in Australia. And this is just, so we're not selecting any period, we're just taking all of the available data. And it says that most of Australia has got wetter. There's a big bit in the middle where there's no data. The bits that have got drier, the dots on it, by the way, are statistically significant. So you see that if it's a big trend, they tend to be statistically significant. If it's a small trend, not so. So statistically significant is Southwest Australia, parts of Western Tasmania, and pretty much the arid core of Australia is wetter. And actually so is most of New South Wales. It's very important here to look at subannual and to think about seasonal. And seasonal is really important, because imagine you had a place with a constant amount of rain, but for some reason, there was a shift towards summer rain and away from winter rain. So in general, summer rain tends to favour vegetation. And as a consequence, there'll be less water in the rivers. Winter rain is the opposite. Winter rain tends to favour rivers, and therefore there'll be less for vegetation. And the trends across Australia are pretty much nearly everywhere is getting more summer rain, even Southwest Australia. Most places are either getting the same amount of winter rain, although many places are getting less. So we've got these long-term trends in rainfall with a shift towards summer, away from winter rain. So taking the naive view, over the area that the Black Summer, most of New South Wales, for example, we would expect increased vegetation productivity and decreased stream flow. And in fact, both of those have been observed. So that's kind of setting the scene to what the long-term wetting and drying is. So basically, most parts of Australia are wetting up, and they're wetting up because they're getting more summer rain. So let's now go back and have a closer look. So this is Perth, and we want to try and summarise what we see. So the first thing to note is that the minimum rainfall that you experience in Perth hasn't really changed that much. Dry years, there were plenty of dry years earlier in the record. What's changed is that since about 1965, there's simply no wet years. And of course, so what's changed is shown at the bottom there. The distribution of rainfall has changed, but we've got pretty much a constant minimum. But now the variance is now lower and the mean's lower. So in Perth, the rainfall is now less variable from year to year than it used to be, and there's less rain. Let's go back with that view and look at New South Wales, and it immediately strikes you, New South Wales is the opposite of Perth. In New South Wales, the first half of the 20th century, there were very few really wet years. All of the wet years are since 1950. So in New South Wales, we've now got a slight increase in the mean rainfall, but it's become more variable from year to year. And that's really important because things like droughts and floods and fires are about variability primarily. So now we're talking about variability. We're not talking just about wetter and drier and hotter. We're just thinking about variability. It turns out, if you have a close look, that in New South Wales from 2010 to 2016, it was exceptionally wet. It turns out that's the third wettest 7-year period in the record. And it was followed by the driest 3-year period in the record. So 2010, 2016, exceptionally wet, as were the intervening years. And then 2017 to 2019, the driest 3 years. Now, this will turn out to be very important. Just looking in more detail at the seasons, the distinguishing feature of that drought was actually 3 dry winters in a row. And the other distinguishing feature was in 2019, there was incredibly low spring rainfall. So we'll come to that in a minute. If you look at the record for New South Wales as a whole, there are actually at least 4 years that were drier than any year in that 2017 to 2019 drought. For example, 1919, 1940, 1982, 2002, they were all drier. But each one of those years was followed by a wetter year. So if you're a farm family and you're trying to grow winter wheat, your experience would say, oh, well, if we miss that winter, we'll get it again next year, not to worry. Well, this time that wasn't the case. And there's never been 2 in a row before. And this time we had 3 in a row. And if you assume that those events are independent, and I'll present some evidence in a minute that they were, then that's roughly, because each one of those years is in the lowest 10% of years for rainfall, it's roughly a 1 in 1,000 year occurrence, which is exceptionally rare. Is it climate change? Yeah, possibly. But it need not be. Looking in more detail, that's the same plot. The one at the bottom is what's called the autocorrelation function. And this is a thing that you use to investigate whether there's any structure in the time series. And the dotted lines, the horizontal dotted lines, are 95% confidence intervals. And what you do is you look at the rainfall time series as a function of lag. So you shift it by 1 year and then you calculate the correlation. Then you shift it again and you calculate the correlation. And you can see that all those correlations are about 0 within 95% confidence interval, which means that it's essentially a random time series. And it also means that it's stationary. So 3 dry years in a row is exceptionally rare, but it's not impossible. So the answer to the question, is there anything strange? The answer is no, not really, except there were 3 in a row. And we'll keep that in the back of our mind. For those who are not familiar with autocorrelation, this is the autocorrelation function for New South Wales temperature. So the same interpretation holds, and you can see that the first 12 lags are all statistically significant. So that's actually a textbook example of a non-stationary time series, whereas the previous one was a textbook example of a stationary time series. What about annual rainfall? Anything strange? No, not really, except 2019 was actually, not only was it the hottest year on the record, but it was also the driest. But other than that, there's nothing in the time series that would lead you to conclude that there was something really strange going on. So this is the significance of the dry spring. So that's again from August 2019 to the end of January 2020, 6 months. And over those fire regions, it was in the lowest 10%. So the lowest 10% of springs on record. So what happened? In 2007, the drought started very sharply, much sharper than you would think possible, following a very wet period. And I don't know if you remember, but fires started in winter in that year, and they went out in spring rainfall. And the same thing happened in 2018. There were fires in winter. In 2019, by now we've had 3 incredibly dry years, and there was no spring rainfall. And the fires didn't stop until it rained in late February. So that became the Black Summer. This is all about variability. So to think about that from a fire point of view, it's really important to understand the nature of fuel. So think of living plants. So living plants are not in equilibrium with the atmosphere. They're far from equilibrium. They're saturated or very nearly saturated, and the tissues are at equilibrium with relative humidities of very close to 100%. And living plants are full of water. So they're typically from 50 to 90% water by mass. So fuel, on the other hand, is dead vegetation. That's actually in equilibrium with the atmosphere. And not only that, but the water content of that fuel is actually an order of magnitude less, which is why people order dry firewood to burn in their fires. It's easier to burn. You don't have to vaporize the water before you burn it. The other thing that happened, those of you who've been bushwalking in southern New South Wales or Victoria at any time in the last 15 years will know that the forests are full of these stems. Foresters call them stags. They were killed in previous fires, but they're not yet burnt. Those things are in equilibrium with the atmosphere. So as the drought goes on, it's dry, the air has a very low humidity, that fuel dries out even more, and there's plenty of it. So if you were to design a fire season, this is pretty much it. So what you would want is a very wet period. Well, we actually had an exceptionally wet 7-year period, followed by the driest 3-year period on record. It's kind of like a perfect storm. In terms of climate change, it's not obvious what the link is. There is climate variability, but that variability is actually consistent with what is reasonable to expect. What about the evaporative environment during the drought? Was that more severe than previous droughts? So the first thing to understand is that in a country like in a dry region like Australia, the wetter years tend to be cooler and the drier years tend to be warmer. And that holds in Texas as well. It holds in New South Wales as well. We'll come to the reason for why that is in a minute. But it's expected that when it's the hottest years in terms of anomalies are also drier, or perhaps a better way to put it is the drier years are also hotter. So you often hear, and I've heard it so many times in the press, the warm temperatures during the drought increase evaporation, and that's why everything is so dry. That's actually the wrong concept. It couldn't be further from that. What happens during a drought is there's less water to evaporate. The evaporation actually decreases. It doesn't increase. Further to the point, on the bottom right is an image of a Coolgardie safe. So for those, the older members of the audience might have seen one. It works the same way as an evaporative cooler on your roof. If you have more evaporation, something's cooler. And if you have less evaporation, something is warmer. And that's actually what happens in a drought. Drought is actually one of the reasons for the warmer temperatures, because there's less evaporation, but the heat needs to go somewhere. So it goes into heating the air. So in the field that I work in, pretty much the standard text is Monteith and Unsworth, Principles of Environmental Physics. This is my personal copy. It's the 2nd edition. I've also got the 5th edition. The 1st edition was published in 1960 something. But they all have this same statement: the temperature dependence of evaporation is negligible. The fundamental reason for that is that evaporation is mostly about radiation, humidity, wind, and about vegetation. So what we need, so you hear statements like, oh, because it's warmer, the evaporation will increase. If you're a scientist, nobody goes out to measure the evaporation with a thermometer. If you want to measure it, the 3 key instruments you need are a radiometer, a humidity sensor, and something to measure the speed of the wind, which is very important as well. So we want to characterize the evaporative environment. You go to the Bureau Climate Variability and Change and you look through all the options, and there's no radiation, there's no humidity, and there's no wind. They're not available. So we're kind of stuck. But actually not. There is actually one instrument that integrates all of those things together, and it's called an evaporation pan. And that's a picture of a US Forest Service employee. And to quote the title of the picture, they're gauging the thirst of the air. So an evaporation pan does not measure the evaporation from the ground. Get that out of your mind. What it does is it tells us the thirst of the air. And if you want to know about the thirst of the air, it turns out you've come to the right place. So myself and a whole range of ANU and CSIRO colleagues have done a whole lot of work on this. And the picture in the top right is a likely group. We actually constructed an evaporation pan co-located at the Canberra airport in 2007 and ran it for 3 years, measuring every 5 minutes the radiation, the humidity, and the wind, the things you need to understand it. Now, I'm not going to go into detail about that. I can talk ad nauseum about it, but I won't. Let's just look at the pan evaporation record for New South Wales. That's it there. It's not as long as the rainfall time series, but you can see very clearly that the thirst of the air has not increased. And actually, as it turns out, it's for a slight decrease. If you look Australia-wide, some places the thirst of the air has increased, and some like southeast New South Wales, for example, and some places it's decreased, like northern New South Wales. The point being that it's spatially variable. But the real point is that the trends in this thirst of the air do not follow the air temperature. You can see, for example, on the right-hand side, the plot on the right-hand side at the top, the place with the most extreme warming is actually in southwest Queensland, which also is the place with the highest decrease in the thirst of the air. We don't expect the thirst of the air to follow the air temperature. We know that from first principles. We know that it would follow what's changing with the radiation, the humidity, and the wind. And if you think this is unique to Australia, you need to think again, because pretty much everywhere in the world where this thirst of the air has been measured, it's actually declined. So again, I emphasize the point, it does not follow the air temperature, and we understand the physics of that very well. It turns out that in many parts of the world, the main reason for the decrease in thirst of the air is actually because the wind speed's been declining. And that whole area of science was first discovered using evaporation pans. And there have been also some places where there's been a decline in solar radiation. So let's go back with this newfound knowledge and have a look. So over the course of the pan evaporation record, the most extreme drought years were 1982, 2002, and 2017. And the pan evaporation, at least for the first two, is much higher during those years, but it actually hasn't increased despite the fact that it's warmer. So people who haven't gone to sleep yet and were paying close attention will notice that that trend that I put up finishes in 2017. So the interesting question is, well, why didn't he put up 2018 and 2019? And the answer is, look, I would love to, but I can't because they don't exist. And I'm going to explain why. So Graham Farquhar and I did a paper in 2004 where we looked at Australian pan evaporation trends, and we identified 61 sites that had what we considered to be very high quality data. So good enough for climate change purposes. Claire Stevens, who I think I saw her name on this, is listening. She wrote a paper in 2018. And of those 61 sites that we had identified in 2004, only 21 of them still had data. So 40 of them didn't have good enough data to calculate these regional time series. And the reason is that the PANs are the last manual instrument operated by the Bureau of Meteorology, and the Bureau are under incredible funding problems. So they've set out on a program to put automated PANs out across the country. I think if it wasn't for the Bureau, we wouldn't know that this thirst of the air hadn't increased. And I think if you get a chance, support the Bureau in their endeavours to try and keep this pan evaporation network alive, because it will be critical in years going forward. So just to summarise, I've said that before, 2017 was much warmer than 2002, which was much warmer than 1982, but the thirst of the air went the other way. So the point is, evaporative demand has not increased during drought years. So in summary, the evaporative environment was high in 2017, but we don't know what it was in 2018, 2019. But we do know that the thirst of the air has not increased during droughts, and in fact, on average, it's decreased slightly. So there we would say that if climate change has had an effect, we would have to say that it's reduced the thirst of the air if you subscribe to the view that it's that's what's caused the pan evaporation drop. So going back to the question, why is it so warm during droughts? Well, I've already said that there's reduced evaporation, and that's part of the reason for the warming. The other big part of the warming is during a drought, you get a lot more solar radiation. So dry years, you get a lot more sunlight. Wet years, you get less sunlight. The really important thing about a drought is that during the drought, you get less incoming long-wave radiation. And during a wet year, you get more. And the reason for that is that water vapor is actually a greenhouse gas, a really important one. So drought leads to the situation where the greenhouse effect is temporarily actually less. So is the warming during drought caused directly by greenhouse gases in the atmosphere? No, it's not. We know that because the incoming long wave radiation goes down. The drought may be associated with climate change indirectly, for example, by a change in the circulation, an anomalous change in the circulation, and that's a more complex argument, which I won't get into here. So, taking what we've learned, let's return to the bushfires. Has the increase in greenhouse gases in the atmosphere caused more drought in New South Wales? I would say no, but with the caveat that unless someone could show that the increase in greenhouse gases had caused the rainfall variability to increase since 1960. Will the ongoing accumulation of greenhouse gases in the atmosphere cause more drought? Not necessarily, but I think we should plan for that possibility. The third question, and the answer is really quite different, is will the accumulation of greenhouse gases in the atmosphere lead to more fire? And I think, this is an opinion now, but I think overwhelmingly likely yes. And I'm going to explain why I think that. So bushfires, there's currently a Royal Commission. I think it closed about a month ago for submissions, and there's a whole lot of things being considered, very practical things like air support, social media, etc. I'm not going to talk about any of that. I just want to briefly say something about land planning and then go on to fire conditions. So the image on the right's familiar, it's Malakuta. The image on the left is just from Google Earth. For those of you who haven't been to Malakuta, it's really quite a beautiful place, and it's nestled right on the Southern Ocean and with the most beautiful inlet next to it, estuary, about 30 kilometres long from memory. The thing about Malakuta is it's got one road in and one road out, and there's a whole lot of houses built right next to eucalypt forest. Now, it's not new to suggest this. In fact, this one, the man that employed me when I first came to ANU is Ian Noble, whom I think is possibly listening. It was Ian who first pointed this one out to me. This is the Blue Mountains. So in the Blue Mountains, you've got a highway that goes along a ridge, and then you've got these roads that go off the highway, and the houses are built one house thick along that road. One road in, one road out, and the houses are right next to the eucalypt forest. We kind of know this, but for some reason we ignore it. And I actually heard people say during the fires, people from the Rural Fire Service say, well, I'm not prepared to go and protect those houses because they're just built in such fire-prone places. So there's lots that we can do to improve our land planning in relation to fire. What about more generally? So people often think of fire in terms of ignitions, natural ignitions, accidents, arson. Seems to me there's plenty of ignition sources, and that's unlikely to change. You need some weather. This is not climate, this is weather. In the fires that happened in February in southern New South Wales, I think if you recall, the worst days were actually the windy days. So we had this situation where we were having hot, dry conditions for a week, and then a cold front came, the wind blew up. And once the wind gets under the fire can kind of create its own weather. So there's plenty of that, and I don't see that changing. Drought, we're going to continue to have droughts. They might even get worse. What I want to focus on is fuel, because fuel for this is everything. So what happens to fuel loads in the future depends largely on vegetation productivity. So if you think about vegetation productivity, you're immediately thinking about things like rainfall, maybe solar radiation, etc. But the thing that we're most sure about is that the CO2 is going to increase and we're going to have high air temperatures. When you look at official government projections for rainfall, this is where things get tricky. So this is the projections for the southern slopes, which is the region pretty much from Malakuta all along the southern coast of Victoria and into Tasmania. And basically, some models say there'll be more rain, some say there'll be less. If you average across all of them from memory, I think you end up with 10% reduction by 2050. It's very hard to know what to do with that. It just means there's all these different scenarios and each scenario has a different risk associated with it. So I want to take a much more general approach here and focus on the things that we know the best. So we can say that the vegetation productivity depends on the transpiration and what we'll call the water use efficiency. And it turns out, we know from work mostly done at ANU, it turns out, in the Research School of Biological Sciences, that water use efficiency is very sensitive to the CO2 and the vapor pressure deficit. And basically it increases with the CO2 and it decreases with the vapor pressure deficit. So let's do a calculation. So right now the CO2 is about 415 parts per million, and climate models, and actually myself as well, think that by the year 2050 it'll be about 520 parts per million. So the CO2 is going to go up by about 25%. Over the same period, we expect the temperature to go up 2 degrees. So we expect the vapor pressure deficit should go up about 14%. So we can, with those two numbers, we can calculate what we think the water use efficiency is going to be. And it equals 0.25 minus 0.07. So it equals 0.18. So what we're saying here is that by the year 2050, we expect the water use efficiency to be higher by 18%. It's really important because there were no climate models that suggested the rainfall would drop by more than 15%, and there are also none that suggested it would increase by more than 15%. Now, transpiration is not rainfall. Transpiration is a smaller amount of water than rainfall, but nevertheless, let's just use the 15%. In reality, the changes would be smaller for transpiration. So what's that saying is that for those conceivable futures, the productivity is going to increase by somewhere between 3% and 33%. And if we had no change in transpiration, it would increase by 18%. Which means that there's a reasonable expectation that, variability notwithstanding, fuel is going to accumulate faster. So the immediate question is, what sort of fuel? Could be trees, could be shrubs, could be grasses. This is another question that I owe to Ian Noble, who first taught me this. It turns out to be very important. Some of you may have seen this book, Gamage, the Biggest Estate on Earth. So Professor Gamage is a distinguished historian at the ANU and set out an argument which said that since European settlement, fire and vegetation management have changed dramatically. And the basic argument in the book is that pre-European settlement, Australia was, to quote the title, an estate. So that the trees were more widely spaced with a grassy understory. And so you think to yourself, would that make a difference to those fires? And like, I don't really know. But I was astonished to read last month a paper by a group of leading fire scientists in Australia where they took a new approach and they used a big data type approach to look at all of the various factors that affected large fires. And I've taken figure 4 on the right directly from their paper. So in this work, the big data approach indicated that if you shifted from a woody understory to a grassy understory, there was quite a significant reduction in the frequency of large fires, independent of whether things were dry or the fire weather. And the astonishing thing about that is that they didn't say it, but it actually is consistent with Gamage's argument about a grassy understory. Then, a few weeks after that paper was published, for those of you who haven't seen this Australian story, I would suggest go onto iView and have a look. It was a 30-minute story about a group of Indigenous people who were saying that we're doing this all wrong and that actually we need to go back to traditional burning. And my take on it is that I think maybe it's time to ask for help, because what we're doing is not that good. The other thing about this, is that for people who've got some form of eco-anxiety or people who've seen others with eco-anxiety, this story was really quite uplifting, to the extent that perhaps we won't be ruined. It's worth listening to. I'm running out of time. I just want to briefly point this out because it doesn't seem to be very widely known. If you have a large wildfire in a eucalypt forest which is composed of ash type species, if you don't know what that is, ask Matt Brookhouse. But basically, these are the trees that reseed after a fire. So the fire kills them, they reseed. It turns out that the saplings that grow after grow not in their millions, they grow in their billions, and they're incredibly thirsty. And people have recorded very large drops in runoff after such fires. Now, it seems to be very specific to these reseeders, so not all eucalypt forests do this. So it's important because many years ago, Matt Brookhouse, who's in the Fenner School, and I sat down and did some calculations on this, and we calculated that as a result of the 2003 fires, we calculated that we would expect a drop in stream flow in the Murray River of about 1,000 gigalitres per year by the year 2023. And that's really quite a big number when you consider that the kerfuffle in the Murray-Darling Basin is all about 2,800 gigalitres. So imagine that you take another 1,000 because of the regrowing plants. Now, we actually didn't even consider 2006, 2007, 2009, or the most recent ones. They're just going to make the effect bigger. So it's really quite significant. And this is water that primarily is related to irrigation. Thank you. I'll stop now.
Thank you very much, Michael. And the sound of people clapping, I'm sure, is propagating through the ether. We would like to try to manage questions. So people who do want to ask questions, I'm going to allow people to unmute themselves from this point on. And best thing is probably sort of to raise your hand, and then, for example, Will Howard, you have your hand up. Go ahead, then Nerily, and we'll just
Michael,
do it like that.
That was great. I really enjoyed that talk. It was really informative. But I just wonder how much the lessons that you're deriving from this apply to more managed forestry systems as opposed to natural forests.
You better ask that again.
Sorry, my question was how much do the lessons that you've described here apply to manage sort of forestry plantations as opposed to natural ecosystems. Do you have any insight on that?
Actually, I'm not a forester, Will, so I don't have a huge amount of insight. My understanding is that a lot of the managed forests are Pinus radiata and blue gum. And the whole aim of that is to keep the fire out. So it's kind of a different thing. Does that answer your question?
It does. Thank you very much. Yep, that's good. No, it's very, that was really interesting insight. It'd be interesting to see also just how, you know, it applies to other areas in Australia as well. I'm sure you've already looked at that, and it's probably the topic of other talks.
Neroli, go ahead.
Yeah, yeah, thanks, Mike. That was a really great talk. I wondered, in the example that you worked through in terms of the effect of changing carbon dioxide on the forests and on temperature and vapor pressure deficit, I wondered if you'd had a chance to think about, and I'm thinking particularly of the work that was recently published in Nature based on the carbon and dioxide enrichment experiments from University of Western Sydney and the effect of enhanced carbon dioxide on eucalypt forests, and if you have any thoughts on how that might play into those sorts of that thinking that you showed about forest productivity in the future.
Yeah, actually I do know about that experiment. So what they found is that they increased the CO2 to about the same level I was talking about, and the photosynthesis went up, I think 12% or 14% from memory. But actually what they reported was that there was no extra accumulation of carbon in the above ground part of the forest, and they concluded that the plants must have respired the additional material. I kind of found that surprising. I didn't find it surprising that the photosynthesis would increase. If it's true that the fuel doesn't increase as per what they found, then I think there'll be less of a problem.
Okay, I've got another question from Danny, and then Jenny and Claire after that.
Hi, Mike. This is Danny. Thanks for a great talk. I'm still kind of, my head is spinning. About the fuel question, because it implied in your Aboriginal story, state story, and the findings that there has been a shift from grass to woody vegetation. And you didn't talk much about that, the links between the variability and the shift in the woody vegetation. Could you comment a bit on that?
Yeah, actually, there are many things I didn't talk about. The Indigenous argument is that the shift to a woody understory and to a more woody vegetation is because of the lack of fire. Sandy Berry and I published a paper nearly 20 years ago saying that CO2 should have the same effect to shift things towards woody vegetation. It turns out that's a highly controversial topic, but there's no doubt that worldwide the vegetation has been what they call thickening, so it's becoming woodier. And basically, we don't know why. Or we don't have a formal attribution, but I think that the evidence is accumulating that particularly understory, woody understory, makes fires worse. So I hope that answers your question, all the way from Switzerland.
Thank you.
Am I next, Jenny? I'll ask the question. You say that wind exacerbates fires. Is there any connection between climate change and increased wind, or decreased wind, or specifically higher temperatures and greater winds?
So I indicated that the long-term declines in the thirst of the air were related to a drop in wind speed, but that's kind of like a long-term climatic thing. The wind that really matters, and mattered in the fires in just recently, is actually the fronts, and that comes on a weekly timescale. And I'm not aware of anybody who's looked at that in any great detail, but that would be a very important thing to do. Does that answer your question?
Sort of. Thank you. We need more research as the answer. Yep.
Okay, Claire is next, I think.
Hi, thanks for a really interesting talk, Mike. I just wanted to pick up on something that relates back a bit to the last question. So you talked about this decoupling between temperature and pan evaporation, which obviously is very uncontroversial in a thermodynamic sense. But what about the effect of temperature on vapor pressure deficit? Like, I understand that might have been compensated by things like changing wind speed in the past, but would we necessarily expect that to be the case in the future? And if not, couldn't that lead to increases in atmospheric thirst, as you put it?
Yeah, absolutely. The important thing is to not use temperature as your single metric of everything to do with evaporation, is to look at the things individually. And the pan has the advantage that it integrates all the important things together for you. But absolutely, you're correct. We're running out of questions.
No, we're not entirely. We've got.
Oh, why not?
Okay, C. Bryant is next, and Alex Sengupta is after that, and then I've got one queued up from Giovanni Liguri.
Am I supposed to be reading something?
Pauline?
Hello.
Sorry.
Can I ask?
Sorry.
No, is next.
Sorry. Thanks for a great talk, Mike. I was interested in the bit about variability, and I was wondering, based on the initial bit that you presented, whether you'd looked at the change how the change in the rainfall distribution had affected groundwater recharge. Because one of the thoughts at the moment is that bushfires are linked to groundwater depletion. And so if you've changed the distribution from winter to summer, you've also changed the groundwater depletion that you effectively the moisture profile then in the vegetation. And one of the things that I've looked at in terms of bushfires over time, really adverse years, appear to be when there's a climate anomaly like an Indian Ocean dipole event and or an El Nino on top of a period of drought in a particular area. So these really, really bad fire seasons, 82, 2002, 2003, and 1920 are, and it links in with the groundwater, that you've already depleted the groundwater, and then you have these really adverse events that you draw down the groundwater, which effectively dries out the vegetation because anything that's too shallow can't actually tap into that groundwater, and that makes it more flammable.
Yeah, I think it's important to think that while the plants stay alive, they don't dry out. It's when they die that they dry out.
Yes.
I haven't looked at that myself. I'd be pretty sure that the shift to summer rain would decrease the groundwater. And I think I've seen several talks given by Brad Updike in RSES showing exactly that. So it wouldn't surprise me at all.
Okay.
Hi, Mike. It's Alex here. Can trees be killed by heat stress? So does the increase in heat waves have an effect on mortality?
What actually kills a tree is kind of a very awkward question. Is it carbon starvation or is it water relations? In principle, trees could be killed at temperatures in the mid-50s where the proteins denature. At lower temperatures, I suppose there might be someone else here who might know better. One thing to think about in that is if you go out into a forest and you see a big old tree, that tree has survived everything that nature's thrown at it for 200 years. So it doesn't really answer your question directly, but I hope it helps.
Thank you.
Giovanni, if you're still there, go ahead.
Oh, yes, I'm here. Yeah, thank you so much for the talk. So, as you said, this is a season-long event. So it was quite special. It's the only one that has a name, given a name to the event. So, but do you think that this event that comes after 3 years of important deficit, rain deficit, do you think these 3 years is a kind of it could have been kind of predictable? Like, is it a spatial number, or is it happen, or we could expect these events to come also after the same intensity of the same rain deficit over 5 years? Or yeah, do you think is it a kind of intrinsic time scale? These 3 years is an important number, or is just happen to be 3?
Based on the autocorrelation function says that time series is stationary. So if you sit down and write a computer program, you get the properties of that distribution, and you write a computer program to sample from it randomly and produce time series, you'll find you can produce time series of pretty much anything. So in that context, I think we're dealing with a 120-year sample out of something that's much longer. And I haven't personally seen evidence that would say that the 3 years is special. It seems to me like it's just kind of bad luck.
I see. Okay, thank you.
There's a question on the chat. Mike, would you like me? Oh, someone's put their hand up for it.
I don't actually know where you see the chat.
Oh, down the bottom, there's a bar next to participants in the middle. It says chat. You click there.
I can't see it.
Oh,
Don't worry, Matthias is online and prepared to ask the question directly.
Oh,
I think.
Matthias, fire away.
Well, perhaps not. But
Can you unmute, Matthias?
Sorry, I'll start again. Excuse
there
me.
we go.
Hello.
Hi, Mike. Thanks for a great talk. Yeah, so in several studies we've shown, and other people have as well, of course, have shown that burned area and fire activity in forested environments responds very strongly to fuel moisture content in that landscape. And it's a really marked threshold response. So we see that once fuels dry out to say below 10%, you get a jump in the area burned in that area. And so that is consistent with, you know, some conceptual models we're working with that propose that, you know, fire activity is really a product of several limiting factors that work in a hierarchy, like conditional probabilities. You need fuel first, and then it needs to be dry to burn, etc. So in forests, whether you have more fuel or less fuel wouldn't really matter unless there's also change in the capacity to dry out that fuel. So do you have any comment on that?
I agree more. I agree with you totally.
Okay, that's great. Yeah.
Actually, I've been helping a group in Europe who are redoing the Spitfire model. And they're using that very old concept of the solid concept of fiber saturation point to actually incorporate the thermodynamics of fuel properly. And it seems to have improved their things out of sight.
Okay, that's very interesting.
That fiber saturation point says that the wettest dead vegetation can get is about 25% moisture content.
Mm-hmm.
And once you get, so under that drought conditions that we would have had dry fuel with a moisture content below 10%, and we would have had it in the big logs.
Absolutely, yes. Yeah.
It was so dry for so long.
Yeah, so some analysis we did, we showed that the very low fuel moisture areas were extremely widespread and occurred over an exceptionally long period of 2019, and that was really you know, an outlier in a long time series. Okay, thanks, Mark.
My pleasure.
So there's still a couple of points on the chat, but what I think we should probably do is take the first of those, which is asking you to provide a short summary for the listeners, and then give people an opportunity to bow out, because we've got a lot of people have had to go. So if Michael, if you would be able to just kind of give a couple of words to everyone who's still here about what your main conclusions were, and then I'll pause the recording for posterity, and you can hang around as long as you like, fielding any further questions, and that's just
fine. God, that's a hard question. I forgot what I said. Okay, let me try. The Black Summer fires had their genesis originally in an exceptionally wet period from 2010 to 2016, followed by the driest period on the record, 3-year period. The fires really took off because there was no rain to put them out. There had been rain in 2017 and 2018 to put fires out, not in 2019. There's no evidence that the thirst of the air had increased significantly. The thing was just the length of the dry period just dried the fuels out substantially. There is the possibility of a climate change signal in that 3 dry winters in a row, which is an exceptionally rare event. It's something that no reasonable person should be expected to plan for, but it did happen. In terms of the future, I think the most likely future is fuel will be produced faster. And even if there's no change in the drying conditions, there should actually be more dry fuel because there'll be more fuel. How's that for a summary? Oh, and finally, we need to stop using temperature as a metric of anything in the water cycle because it's not that useful. And we need to support the Bureau of Meteorology to maintain their network of evaporation pans, which is so important to understanding what's happening. So that's pretty much the summary.
Thank you. I'm going to stop the recording at that point, but people can, continue to talk to you as long as you need. That's great.
Oh, good. I want to go to Bunnings this afternoon.